What's up, skater boys and girls? We are going to review today. What a wonderful time of year. Christmas is almost upon us. We've got to do some shopping. We've got to do some shaking of our relatives' hands. You know, you got to see your tia. Got to say, oh, how's Tommy? How's. It's a wonderful season, honestly. We can watch claymation, cartoons. It's going to be great. But before we get into the holiday season, we've got a review for our final. So today we're going to go over our unit on sequences and series. This is going to be super fun. You're going to love it. I'm going to love it. We're all going to have a great time. And then you're going to go practice. And then maybe, hopefully, you'll pass your final. So what we're going to go over today, we're going to focus on a couple of things. We're going to focus on finding the nth term of a sequence. So if I say find the 28th term, then you can find that. Okay. We're going to find the series of a sequence, and we're going to look at some infinite geometric series. So first, let's go look at some vocabulary to make sure you remember all the words I'm saying. All right. First, a sequence is just a list of numbers. So like 1, 2, 3, 4. That's a sequence. Sequences do not necessarily have to have a pattern to them, but the two that we care about for this unit definitely do have a pattern to them. So we'll take advantage of those patterns and do some math with them. A series is just the sum of the sequences in a sequence. Remember, sum is just the fancy math word for adding. So if I want to take the series of this sequence, it would just be this. There you go. Now it's a series instead of a sequence. So not too bad. There are two types of sequences we're going to look at. We're going to look at arithmetic sequences. An arithmetic sequence is a sequence in which the difference between consecutive terms is constant. So that just means that they go up by the same amount each time, like this. It's plus 3, plus 3, plus 3. This would be an arithmetic sequence. This is also an arithmetic sequence. It's plus 1, plus 1, plus 1. So anytime you are adding or subtracting the same amount every single time to get the next number, that's arithmetic. If we have a sequence for adding and subtracting, the other one is probably easy to guess. A geometric sequence is a sequence in which the quotient of consecutive terms is the same. That's a fancy way for saying you multiply by the same amount each time. All right, so times 2, times 2, times 2, times 2, and so on. For an arithmetic sequence, the name of the number we are adding each time, so the name of this 3 is the common difference. And we use lowercase d for the variable. So d is just the amount being added or subtracted. If it's subtracted, it'll be a negative number to get the next term in the sequence. The number or the name of the number that we are multiplying by each time for geometric sequences is called the common ratio. And we use lowercase r for that. If we are dividing, so let's say you have like 8, 4, 2, 1, and we're dividing by 2 each time. Dividing by 2 is the same thing as multiplying by a half. So if you are dividing each time, your common ratio will be equal to 1 over the number you divide by. Cool? Not too bad. All right. So there's all the vocabulary. I'm just going to go ahead and do a few examples with you guys so that you can see how the problems are done, since that's all you really care about anyway. How do I do the problem so that I can pass the test and I can get a good grade, and then I can go to college, and then I can get a job that I'll probably not even like, and then change to a different job in my 30s anyway. Let's figure out how to do that. So there are some formulas you are going to need. There's actually a bonus fifth formula. It's on the slide we're going to need it on, but it's a not generalization, but a special case of this sequence or this formula. But let's go ahead and peek at these just to kind of get the important information out of them, and then we'll go do the examples. So here are the formulas for sequences. These will help you find the nth term. Okay, so this one is for arithmetic. That's why it's got an A there. So if we want to find term n, and n is just saying like what number, how many numbers through the list have you gone? So if I say, what's the 8th number in this list? N would be 8 in that case. So an, or the 8th number in the list, is equal to a1. This is just the first number in the list. So it's your starting number, plus your common difference. This is the number you're adding or subtracting each time, times n minus 1. And again, n is just the term number. So if you want the 8th number, n would be 8, right? So we take the first number, add the amount we're adding or subtracting, times however many numbers we're going through the list, minus 1. This one is for our geometric sequence. So if I want whatever term number, if I want G13, I take the first number in the list, G1, times the thing I'm multiplying by to the n minus 1 power. This will give me the 13th number in the list. Okay. Let's look at our series formulas. These are how we add up all the numbers that you get in these two lists. So this thing, don't trip about that. This is just a fancy way to write a1 plus a2 plus a3 plus ... plus an. This is the shorthand for that. So it's saying if I add up, that's what this big sigma is for. If I add up all the arithmetic terms, starting at the first one, going to the term n, the answer I get when I add them all up will be whatever that number is. So this number is n, the number of terms you're adding, the number of terms you're adding together, times the first term plus the last term. And then take that number and divide it by 2. That'll give you the sum of all the numbers in this list. Okay. Likewise, for a geometric sequence, the sum of all the geometric terms starting at the first one, ending at whatever one you want, n, is the first term times the thing you're multiplying by to the power of n, which is the same as that number right there, minus 1, divided by r minus 1. Okay. This thing does not really work if r is 1. If r is 1, what that means is you're going to have a starting number. Let's say it's 4, and then times 1. If r is your common ratio, it's what you're multiplying by. 1, 1, 1. You see what I mean? It's boring. It doesn't really work. So it'd be the same as if d were 0. It's kind of boring. So just a disclaimer, it doesn't work. Whoops, I didn't want to move that. Okay, cool. So there's our formulas. Let's go look at some examples to really teach you how to use these again. Okay. So we're just going to go through in order. We'll start with the series, then we'll do some sequences. Let me just make sure my pens are all, looks good. Okay. So we want to find the 23rd number in this list. 13, 40, 67, 94. So what we need to do is we need to find the first term, the thing we're adding each time, and which term number we want to get. You need those 3 pieces of information to be able to solve these problems. Then we'll plug them into this, and then that will give us the 23rd term. So A1 is given to you. It's that first number right there. So A1 equals 13. Now to get the number that you're adding each time, you just take any number in this list. Let's take the second one. And then you subtract the number before it. And then that will give you your common difference. So this will be 27. Okay. So D equals 27. And then N is what term are you looking for? It tells you in the problem. We're looking for the 23rd problem. So N is 23. So what we're going to do is we're going to plug these three numbers into our formula, and then we'll simplify. So we have A23 equals A1 plus D times N minus 1. So 23 minus 1. Okay, so this is 22. And we're going to multiply that by 27. So 22 times 27. Whoops, that's not it. Is 594 plus 13. So A23 is equal to 607. And there you go. So if you go 23 numbers out in that list, the number there will be 607, in case you cared. Not that you asked, but you know. So there you go, pretty easy. Nice first example. All right, let's look at a geometric sequence. So we want to find the 15th number, and what we need to know is the first term, the number we're multiplying by, and which term we're looking for. So G1 is 2. And R, we have to find the common ratio. So what we're going to do is we're going to divide to find R. So just like we took any number in this list and subtracted the number before it, for a geometric sequence to find R, you're going to take any number in the list and divide by the number before it. So let's just take negative 16. So negative 16 divided by the number before it, positive 8. This is negative 2. So R is negative 2, and we're multiplying by negative 2 each time. And then N is given to us in the problem. It's 15. Okay. So now we're going to just plug these into this. We'll use a calculator to do the exponent, and then that will tell us the 15th number in the list. So G15 equals G1, which is 2, parentheses, negative 2 to the power of 15 minus 1. When you type this piece into your calculator, because the 2 is negative, you want to be really sure to put parentheses around it. Otherwise, it might mess up signs if you're not careful. So we're going to do negative 2 to the power of 14, because 15 minus 1. This is equal to 16,324. And that's being multiplied by 2. So we're going to do times 2. So G15 equals 32,768. So that will be the 15th number in our list. Not too bad. So there are our sequence examples. That's just finding a number in the list without having to actually multiply by negative 2 15 times, because typically what I do is I ask for like the 27th number, and then I have kids type it in their calculator 27 times, and almost without fail, like a third of the kids get it wrong because they count the wrong number of things. So this is just a more reliable way to get the answer. If you type times negative 2 and then just hit enter 15 times or 14 times or however many times it takes to get to the 15th number, it'll be correct. But if I said, what's the 1,057th term in the list, you wouldn't want to hit it that many times and count, because I guarantee you'd mess up. So you want to use the formula. All right. Let's look at a couple of series examples. So now what we want to do is we want to take all these numbers in the list, and then we have to add them up. So you could find a list of all 20 numbers, right? You could do 11, 13, 15, and put plus signs in there and just hit the equals. That works. But for argument's sake, let's go ahead and use the formula. So for our formula, what we need is n. It's right there. N is 20. We need to know the first term in the sequence. So A1 equals 1. And unfortunately for arithmetic series, you need to know the last term also. So we need to find A20 as well. To find A20 for this formula, we have to use this arithmetic series, or, ooh, wow, that's a big typo. This should say sequence. This arithmetic sequence formula. So let's find A20 first. So A20 equals A1 plus our common difference times n minus 1. Our common difference here is what we're adding each time, and I think it's pretty obvious that it's 2. So this could be 1 plus 2 times 19, 1 plus 38. So A20 equals 39. Okay, now we're going to take these three numbers and we're going to plug them into this formula to get our answer. So the sum of all 20 terms here is 20 times 1 plus 39 over 2. So this is 20 times 40 over 2. 2 and 20 reduce, so this will be 10, and 10 times 40 is 400. So if you add up all the odd numbers for the first 20 of them, you get 400. Cool. That's pretty neat. All right, so not too bad. The worst part is finding an because you have to use the sequence formula, but you know, you're big kids now. You're gonna have to get used to life being hard. All right, 2 more examples, then we're done. So now we're gonna look at our geometric series example. This one's a little easier than the arithmetic because notice we don't care what Gn is. We don't have to find the last term in the sequence, so not too bad. So Gi is the first number in the list, so it's gonna be 2048. R is what we're multiplying by each time, and that might be a little not obvious here. And N is going to be the number they tell us in the problem, so 20. It's how many things we're adding together. So let's go find R. Let's just take any number in the list. Let's use the smallest ones. 256 divided by the number before it, 512. This reduces to 1/2. So we're dividing by 2 each time or multiplying by 1/2. So now we're going to plug these 3 numbers into our formula, and then that'll tell us what do we get if we add up the first 20 numbers starting at 2048 and then cutting in half each time. So we're going to have the sum of Gi up to the first 20 starting at 1 equals 2048 times 1/2 to the power of 20 minus 1 divided by 1/2 minus 1. All right, so now we have to go clean this thing up a little bit. We're definitely going to take advantage of our calculator here. So 2048 times, we're going to put this chunk in our calculator so that we don't have to do it by hand. And I'm going to get a decimal here, I think, because, you know, it'll be easier. Ooh, I don't want that as a decimal, actually. Let's see. Let's see if I can get it not as a decimal. It's pretty ugly. It's pretty ugly either way. All right. we're going to put it not as a decimal, but you're not going to like it. It's 1,448,575 over 1,048,576. I told you weren't going to like it, but again, you're big kids now. You got to get used to not being happy. And this is negative 1/2 on the bottom. Okay, so now all we have to do is multiply this ugly number by 2,048. And then we're going to divide that by negative 1/2. So what we get when you plug this whole mess into your calculator is positive 4,096. That's pretty cool. That's actually a really nice answer for having such an ugly fraction, huh? So there we go. Cool. What I would probably do is try and just plug that whole thing into your calculator, especially if you have those nice Casio ones from school. Your Casio one should be pretty easy to plug this entire thing into, to be honest. I would just be really careful. Maybe do your fraction thing first, like that. And then just make sure you include some parentheses. Be careful, you know? Cool. There you go. Nice example. All right. Last one, and then we are done. This one's actually probably easier or less scary looking than this one. It's got some nicer numbers. So what we want to do now is an infinite geometric series. What infinite means is that we're going to take infinity number of numbers and add them together, which might seem a little like, how do you add an infinite number of things together? But it works out, so it's cool. It reminds me of that SpongeBob meme where it's like, I think he says, hey, do you want to see me run around the entire planet? And then nothing happens. And then he says, hey, do you want to see me do it again? Cracks me up. That's what we're going to do here. After class today, go up to your mom or your dad or whoever you live with and say, hey, do you want to see me add an infinity number of things together? Hey, do you want to see me do it again? See if they... I wonder, do your parents have sense of humor? Would they laugh or would they just like be confused and be like, leave me alone? Interesting question. Anyway, let's do the example. Look how easy this is. When you add an infinite number of things together, isn't it crazy how the formula gets easier? So all we need is the first number and then the thing we're multiplying by. So the first number obviously is 9. So G1 equals 9. And then here, what we're multiplying by, we're going to take any number, 3, and divide it by the number before, 9. That's 1/3. That's R. So we are multiplying by 1/3 or dividing by 3 each time. Okay. Now we're going to just plug our numbers in. So the sum of all these numbers, in case you're not sure what they are, it's like 1/3, 1/9, 1/27, and so on. So we're going to add an infinite number of these tiny fractions together. Equals 9 divided by 1 minus 1/3. So this is going to be 9 divided by 1 is 3/3, right? So 3/3 minus 1/3 is 2/3. And when we divide by a fraction, we know that we can just flip the fraction and multiply instead. So 9 times 3 is 27 over 2. And I would prefer it if you left your answer like that. But you could also write it as a decimal, which is 13.5. There you go. So if you add an infinite number of things being cut by 1/3 or into 1/3, starting at 9, you get 13.5. So cool. Awesome. Isn't it crazy? Look at this. If you take 9 plus 3 plus 1, that's 13. All of these fractions combined for forever is only a half. That's so crazy. Isn't math wild, you guys? That's wild. I feel like I'm watching Nick Cannon's Wildin' Out right now or something crazy like that, you know? Or like a SpongeBob episode. So crazy. Anyway, hopefully this really refreshed your memory. Hopefully it wasn't too bad. Hopefully you've already liked and subscribed. If not, make sure you like and subscribe and hit the bell icon for notifications. See you guys later.